Hello everybody, this is Mr. Stevenson again, and today we are continuing our introduction to calculus. We're going to talk about instantaneous rate of change. Last time we talked about average rate of change in the secant line, and we're going to use that, we're going to build upon that to try to figure out this instantaneous rate of change. So we're going to actually look at an example that we've talked about. We looked at it in the practice set for the test, the review for the test that we just took. It was this problem with a pot of water being heated to 100 degrees Celsius and then left to cool in a room. With the thermostat set at 21 degrees Celsius, and we recorded this data. And using an exponential model, we came up with a function that looks like this, right? And so, in case you didn't figure this out before, anytime we're talking about a law of cooling, this number over here is always going to be the room temp. This number here is going to be the starting temp minus the room temp. And then this number here changes based on how, like, this volume of the object you're talking about. So this rate will be dependent on what we're talking about. What, is it water? Is it metal? Is it huge? Is it small? That kind of thing. But these two numbers can always be based on that. We already did that part, so we're not going to talk about that. What we're going to talk about is, maybe you want to answer this question: at what rate is the temperature changing? So we want to know, like, well, how fast is the temperature changing as time goes by, right? Is it changing by 2 degrees Celsius per minute, or 5 degrees Celsius per minute, or like how fast is it changing? And so that's where this question can't actually be answered like that easily, because let's say I wanted to consider these 2 points, right? What is the rate of change of the temperature between t equals 0 and t equals 10 in the first 10 minutes? Well, the rate of change would be, we're going to call this function c of t, so it'd be c of 10 minus c of 0 minus over 10 minus 0, right? It's basically y2 minus y1 over x2 minus x1. In this case, it's 83 minus 100 over 10 minus 0, which is negative 27, negative 17 over 10, or negative 1.7. Remember your units. These are degrees Celsius and these are minutes. So it's negative 1.7 degrees Celsius per minute, meaning the temperature is going down by 1.7 degrees Celsius every minute. And so you might say, hey, all right, that's how fast the temperature is changing, is negative 1.7. But if you consider a different time interval, let's say this one between 10 and 20, then we would do c of 20 over c of 10 minus 20 minus 10. And in this case, we would get 70.5 minus 83 over 10, right? 20 minus 10 is 10. Let's do this real quick. 70.5 minus 83. All right. 70.5 minus 83 is negative 12.5 over 10, which means our average rate of change here is negative 1.25 degrees Celsius per minute. And you can see the rate of change has changed, right? It's not a constant rate of change, it's changing. And so you could even do this for every single value in here, and you'd notice that it gets different, right? Because these are average rates of change. And to illustrate what's happening here, I'm going to go on Desmos, kind of show you what we're doing, but we're going to actually graph a line with these. Remember, this is the slope of this secant line. And also remember from previous chapters that I can write the equation of a line using some like this equation, right? This is point slope form. This here is going to be our slope, which, remember, the slope came from doing f of x2 minus f of x1 over x2 minus x1. So that's our slope. And then we're going to do x minus x1. And then the y2 coordinate is the same thing as f of x. Well, whatever function we do, whatever these two should match, right? So I'm going to just show you on Desmos real quick how what this looks like graphically. So here's our function, and we came up with this model. And so in that first problem, we figured out the average rate of change between 0 and 10. So this is what that slope would give us using the function itself. It's a little bit different than using the points. You can see it's a little bit different here. But if I want to write the equation for this, I would do y minus one of the y coordinates here. So let's say c of I don't know, let's do 10. And that's going to equal the slope, which is given by the, that formula, times x minus 10. And if you see, what that's done is that's created this secant line that passes through those 2 points on the actual function, right? And so the slope of this secant line tells me the average rate of change of this function between those two. And so I could do the same thing with this here, and instead of between, for the next one I want to go between 10 and 20. I want to figure out the average rate of change between 10 and 20, so I just changed these to 10 and 20, and then I'm going to go and change this to 20 and 20, and you can see that gives me the average rate of change between the secant line between 10 and 20, right? And again, the number represented by this is the slope of that line, right? And so we could even figure out, well, okay, what's the average rate of change from 0 to 60, right? So you do the same thing, you do the same idea. The rate of change between 0 and 60 would just be 60, 0, 60, 0. The total average rate of change is about -1. And then if we actually want to find out that equation of that line, it looks like this, and you can see it's a secant line passing through those 2 points, and it's the average rate of change, right? So in the first hour, the average rate of change is about -1 degrees Celsius per minute, but again, that doesn't capture the actual rate of change throughout the whole thing. So that's where we get into this idea of, well, what if I wanted to know exactly how fast was it changing at t equals 30, right? Exactly here, what was the rate of change? And for the sake of this, that's fine. So how would we go about doing this to know it at exactly 30? Notice it's not an interval, but it's just like a fixed time, right? So you could say, okay, well, let's find the average rate of change from 20 to, from t equals 20 to t equals 30. And then we can find the average rate of change from t equals 30 to t equals 40, right? And what that will do is it'll tell you the average on both sides, right? It'll tell you, the slope of this one and the slope of this one, and you'll know you're kind of close, but again, it's not going to be perfect. So I'm gonna go ahead and do that on here. I'm not going to do the line. I'll just do the average rate of change. So we're going to go from 20 to 30, or 20 to 30. So the average rate of change between 20 and 30 is -1.04, and the average rate of change between 30 and 40 is -0.186, right? And so at 30, it should be somewhere close to those, but not exactly. So here's what we could do: is we could say, okay, well, this gives me a generally good estimate, right? Based on that it's close to 30. I'm going to go back to this C of let's say 30, and I'm gonna do the equation just so you can see what's happening. What if, so you can see this is giving me that line. What if I found the equation that's even closer, between 2 points, even closer to 30? So let's go between 25 and 30, right? What if I find the average rate of change between 25 and 30? Don't you think this is a better estimate of the actual rate of change at 30? You can see that, we're still talking about a secant line, but the slope of this line is closer to the slope of the line at that function. And then I could say, okay, what if I got even closer to 30? What's closer to 30? Well, how about 29? What if I found the average rate of change between 29 and 30? You can see that this is even a better approximation. And I'm going to go ahead and copy this down here so you can see what it is. So it's -0.9131. Well, what if I did 29.9 and 30? That's -0.9219, like this, right? What if I got really close to 30 without actually touching 30? You can see that this number is approaching a fixed value, right? Like we're getting, where this is not changing anymore, no matter how close to 30 I get. Finding the secant line between a point really close to 30 and 30 is approaching a very fixed number. So then you might say, well, what if I just plug in 30? Why can't I just do the secant line between 30 and 30. Well, what do you think is going to happen? You're going to get undefined, because in the denominator you get 0. So you can't actually find it using the point itself, but you can find something using a point very, very close to it. Right? And so if you notice, if I actually plot this line, basically this is a line that's just touching there and then coming off. It's what we call a tangent line, right? It's not a secant line really anymore. It technically is, because it's touching 2 points. But if we can get this point so close that the 2 points are basically indistinguishable, and I have what I call a tangent line that just touches at 1 point, and the slope of this tangent line is this, right? No matter how much closer I get, this number is not going to change anymore, right? We have found that that slope is approaching negative 0.9. Sorry, I have one too many. Yeah, negative 0.92. And so that's what we found, is the slope of a secant line. Or sorry, slope of the tangent line. So I'm going to go and draw that on here. So tangent line is a line that touches the graph at exactly 1 point, and it has the same slope as the graph at that point. So what is the rate of change of the temperature at T equals 30? Well, based on what we just did, we got the rate of the change, the slope of the tangent line is negative 0.92. So you'd say negative 0.92 degrees Celsius per minute. That's exactly at T equals 30. And you could do the same thing for, okay, now I want to know it at 50. I just change this to 50. And I get really close to 50, right? So it's just 49 and 49. And again, I have to change this to 50 in order for it to actually be that. 50, 50, 49, 49. And I'll start with something, let's start with something a little bit further away so you can just kind of see this process again, right? So the average rate of change between 40 and 50 is negative 0.6. If I get closer to 50, we get negative 0.601. If I get even closer, we get negative 0.5729. If I get even closer, we get negative 0.566. If I get even closer, negative 0.566. And you can see that that number is not changing anymore. So I can basically estimate that the slope of the tangent line, the instantaneous rate of change at 50, is negative 0.566 degrees Celsius per minute. And so that's what we call instantaneous rate of change, is the rate of change at a point, which can be found by finding the slope of the secant line as you get closer and closer to that value. Okay, I'm going to show you a couple of different ways to think about this. So what we're doing is we're trying to figure out the slope of a tangent line, that just the slope of the line at a point. What we end up doing is we end up figuring out the slope of the line, the secant line between 2 points, right? So basically what would happen is this would be x2, this would be x1, and then the y coordinate would be, this would be f of x2, and the y coordinate of this one would be f of x1. And so the slope of this line is f of x2 minus f of x1 over x2 minus x1. And what we saw is that the slope of this line becomes the slope of the tangent line if x2 gets close to x1, right? So what we would say is that I'm going to introduce you to a notation. We'd say as x2 gets close to x1, right? If I find the limit, which is basically just making x2 get close to x1, then this will become the slope of that secant line. Another way to think about this is just have 1 point, right? This is the point we want to know here. Call it x1. Then my other point is just, we'll call this h units away, right? So this, we're adding h, so this is x1 plus h. Then the y coordinates up here are f of x1, and the y coordinate of this one is f of x1 plus h, right? Plus is just plus a little bit, right? And then what our goal is then to make this h go to 0. So again, I'm going to use this notation. I want this h value to go to 0, but the slope of this line is now just f of x plus h, right? F of x plus h, the slope of the line, minus f of x over x minus h. And what we do is we make this h smaller and smaller and smaller, so these 2 points become closer and closer together. All right, so to look at an example of this, this is one of the things you're going to be doing on Desmos or Delta Math just to practice, is we have our graph here. We want to move the blue dot as close to the yellow dot at -3 as we can. And what it's going to show you is, here's the secant slope is what we've been talking about. This h value is the distance between these 2 points in the x-axis. It's represented by this green. And the number down here represents, that formula I just talked about, where it's, f of x2. x2 is basically just, x1 plus a little bit, right? x1 is here plus however much, that h value is. And then what we're going to do is we're going to move this point closer and closer and closer. And you can see that this number here changes by a little bit, by a little bit, by a little bit. And you end up with, if you get close enough, you end up with the slope of the tangent line, right? Right now h is 0.01. We could zoom in even more. And you can make this even closer. Now h is 0.001. And you can see that this number is approaching a fixed value, right? Like we're getting closer and closer, a better and better estimate of the slope of the tangent line. Notice only these digits are changing now. So like this is a good estimate of the slope of my tangent line, which again is the instantaneous rate of change. Okay, so I'm going to go through some examples that you see on Delta Math. You don't have to watch these if you feel like you can do the Delta Math problems without it. I just wanted to show it to you so you can see it if you need it. So the first one is this. We're given a function, and there's a graph in Delta Math. We don't need it right now. We want to determine the slope of the secant line at each of the intervals in the table. So we're going between 3 and x. So you can imagine if you have some graph. Here's 3, and then the first value is going to be between 3 and 4. So when I'm finding this one, I'm finding the slope of the secant line between 3 and 4. And again, the way we're going to do that is we're going to do f of 4 minus f of 3 over 4 minus 3. Right? To figure out f of 4, you got to take this 4 and you got to plug it in up here. So 4 squared is 16, minus 4 times 3 is 12, minus 18. That's going to give me 4 minus 18 is negative 14 over 1. So in this case, the slope of the secant is negative 14. Now we're going to go to 3.1, right? So we're going to make this second point even closer to the original point, right? We're going to put it here, and we're going to find the slope of that secant line, right? And again, it's just going to be f of 3.1 minus f of 3 over 4 minus 3. F of 3.1, you need a calculator for this, right? So you can go to Desmos or use use some other calculator, but you put your function here. Let me pause so I can get it on here. Okay, we got Desmos up now. So I'm going to do f of 3.1, which is negative 17.69. So if I was actually writing this out, negative 17.69 minus f of 3, which is, we said this before, negative 18 over, oh, you know what? I messed up that first one. I'm going to have to go back and do that again. Over 1. And on Desmos, it's honestly just easier to do it like the whole thing. So we're getting 0.31. What I messed up here is I forgot to subtract f of 3. F of 3 is, we just did it and I forgot it already, negative 18. And so if we actually get this, we're getting 4, right? So this should be 4, not negative 14. Hey now. 4. And then this one is 0.31. And we do the same thing here, right? I don't know if you're on Desmos, it's a lot easier. We're doing f of 3.01 minus f of 3 over, I messed this one up too. This is not 4 minus 3 anymore, it's 3.1 minus 3, which gives us 0.1. So I have to divide this by 0.1, which gives us 3.1. My apologies for the confusion on that. So then let me actually do this one. It's going to be f of 3.01 minus f of 3 over 3.01 minus 3. So if we do f of 3.01, we get negative 17.9699 minus, this was negative 18 all over 0.01, right? And then that's going to give us that, and if we divide that whole thing, we end up with 3.01. And so maybe you can notice a pattern here. What do you think is going to happen if I do this? Well, I'm probably going to get 3.001. And then so you could imagine, well, what if I did something extremely close to 3? You're going to get a secant slope that's extremely close to 3 as well, right? And so you can see that as the closer we get, we're just going to start approaching a fixed number of 3, which is interesting. Okay, the next one is just the same thing, but in a different way. This is the one where they're telling you an H value. So they're just saying, okay, we're finding it between an X value of 1, right? So we're on here at 1. Here's maybe our function. And in the first case, it's saying H is 1, meaning we're going to be, that H value here is going to be 1 unit, meaning we're going to be right there. So our two values are going to be f of 1 and then f of 1 plus h, and in this case h is 1, so it's f of 1 plus 1, which is f of 2, right? So it's just a different way of doing it. So in this case it's f of 2 minus f of 1 over 2 minus 1, which again you got to go back up there and plug it in. Let's go ahead and write this out. Plus 4x minus 38. So basically what we're doing is we're doing, and I'll go ahead and write it this way so you can see, we're doing f of x plus h minus f of x over x plus h minus x. And now I kind of want you to notice what would happen if I actually did it this way. But if I add a slider for h, basically I can just say, okay, if h is 1, then oh, and then in this case x is 1 because we're doing it at 1, right? So let's go change all these to 1 because we're centering at 1. If h is 1, then I get 10, right? So again, if I did this, I would get a value of 10. When it's 0.01, it's going to be f of 1 plus 0.1, because that's our h value, plus minus f of 1 over 1.1 minus 1, right? So basically f of 1.1 minus f of 1, you plug them in there, or you get a Desmos. In this case, h is 0.1, and you get a slope of 8.2 in that case, right? If you work this out, you should get 8.2. If I do 0.01, I get 8.02. If I do 0.001, I get 8.002, and you can see the closer you get to 1, right, the closer you make this value to 1, the closer to 8 this will get, right? So you could basically just assume that the slope of the tangent line is 8 at that value. All right, I hope this helps. Please reach out with any questions.